routine access by external users from other academic institutions. So I'm going to just talk a little bit about the historical overview of the National Centre. Okay, so it was actually founded by the vision of Professor Peter Robson, who came back from a sabbatical year in Stanford University in the sort of mid to late 60s. At that time, they were working there on traveling wave amplifiers where they were seeing that they could get high gain. So now, when he returned to the UK, he sort of set up some basic optical lithography and processing facilities. But what he found was that he could not get hold of this gallium arsenide material that very few people had heard of at that time. So they put in a bid to our research councils to ask them to build a clean room and to build our own equipment for making these semiconductor materials. Now, in the early days, these were pretty much Keith Robinson exercises where we had to actually build the heater stage by winding resistance wires. We had to build the, we had to blow glass, which would then encapsulate this furnace. We had to gold plate things ourselves. So everything was done by extremely good research workers and technicians. And this enabled us to start doing some basic research into semiconductors. At that time, the government decided to look at what facilities were lacking in universities. And they wanted them to say that they wanted a few centers to have high quality, expensive facilities where they could then act as a center to provide this expertise to other UK universities. So the important remit was that other research workers from other departments, other universities would be entitled to use these facilities because the funding came in centrally from the research councils. So without reading all this text, the main thing is to understand is that funding was given to Sheffield for a relatively small amount of money, about $1 million ringgit in today's million ringgit, for 4 years, of which half of which was roughly for equipment. And then, we could appoint a couple of postdoctoral research workers and one technician. And the starting date of November 1978 was done. So we started off with that relatively modest amount of money, and we then built 2 LPE furnaces and started to grow gallium arsenide layers on semi-insulating substrates. So the first 2 people to start this activity were J.P.R and Drew Nelson. For those of you who are in the 3.5 field, Drew Nelson is now currently the is the CEO or the owner of IQE, which is the world's largest commercial epitaxial sort of organization. So they are based in Cardiff and in America. So clearly, he took this idea of a central facility for growth and sort of commercialized it. So, what are the scientific achievements for the sort of this central facility? And I'll touch on these in a little bit more detail as the talk progresses. But this facility gave rise to many world firsts, record-beating results in terms of material quality or devices such as lasers, modulators, transistors, photodiodes, and solar cells. So there have been well over 1,000 journal papers and 1,500 or so conference papers at least to come out of the facility over the last 25 to 30 years. Taking a snapshot of a 25-year period, over the first 25 years, this facility supported something like 274 externally funded grants, and we grew about almost 9,000 wafers. Okay? Now, the 9,000 wafers is not in itself a very impressive number when you think that large epitaxial foundries are churning out huge numbers of wafers every month. They have multi-wafer reactors and they can produce many, many wafers if they're working 3 shifts a day. What you have to remember is each one of this is a custom designed wafer where each wafer is having to be designed to solve a particular technological problem. So we take a long time to produce a wafer to a design that is given by one person. So the facilities we have now are very impressive, but just to take you back about 30 years to show you some of the facilities we had, it was a very small, clean room we had. A lot of the things that you see there were built by us because there were no companies existing to actually commercially supply us with these ready 3.5 products. So this in 1981 is the world's first commercial MOVP reactor. MOVP reactors existed but only in research labs belonging to defense companies and to 1 or 2 R&D companies. But you could not go out and buy one from a company. Now there are probably about half a dozen in the world who will do whatever you want. But this is the first one, and they had to come and talk to us, and we helped design it in parallel. It was a very small one. It could grow 1 2-inch wafer. As time progressed, we started to add more and more of these furnaces, and then we found that the controls that were required in the sort of early 80s, people were starting to say that this liquid phase epitaxy samples were too small. We could only grow 1 centimeter square samples. People wanted bigger material. They also wanted better uniformity. They wanted better control of the thickness. With the liquid phase epitaxy, you could probably get layers that were about 1 micron thick, and you could control the thickness quite accurately. People were starting to say, look, we want to do work on things like quantum wells, and so we want to get down to maybe 10 nanometers, maybe 50 nanometers, and we could not do that reproducibly using the liquid phase epitaxy. So we decided to invest in a molecular beam epitaxy machine, which you can see in this figure here, this photograph here. So this technique allows us to deposit an atomic layer of a 3.5 material, 1 layer at a time. So we could then build up the layers that way. And this first reactor could grow material like indium phosphide, gallium phosphide, gallium arsenide, and indium gallium arsenide. So we then decided that worked very well. A few years later, because of the expertise we had already gained from growing it by molecular beam epitaxy, we then moved on to get MOVPE, or metal organic vapor phase epitaxy 2. That's the picture on the right-hand side. This, unlike the molecular beam epitaxy, uses chemicals in a gas phase. It uses trimethyl aluminium, trimethyl gallium, and pure arsine and phosphine to provide the group 3s and the group 5s respectively. So these will also allow you to grow monolayer by monolayer, so a high degree of accuracy and precision.